Today in this video we are going to start chapter 5, that is magnetism. The first topic of magnetism is clock roll, suppose. Okay, so here what we are going to do is, we know in previous chapter that through a conductor when current flows, then around the conductor there is formation of some magnetic field, or in other words, when there is a current, magnetic field is also generated. Okay, so here suppose there is a current carrying loop, and in this loop current is flowing in this direction, that is in anti-clockwise direction. In this case the loop will behave like a magnet. One face of the loop will behave like north pole, one face will behave like south pole. Now which pole will behave like which pole? So to get that, we can write here one N like this, and at the tip if you put the arrows, then you can see that the direction of these arrows and the direction of flow of current is same. This arrow and the direction of flow of current same, right? So that means writing N is matching with the direction of current. So the upper surface of the loop will behave like a north pole and the lower surface will behave like a south pole. Remember that. Similarly, if the current is flowing in opposite direction, not like this but like this, clockwise direction, so here if you write N, it will not match with the direction of flow of current, so we can write S here. And on writing S, if you put the arrows at the tip, then this arrow is matching with the direction of flow of current. Okay, this one matching, this one matching. So that means the upper surface will behave like a south pole for this loop and the lower surface will behave like north pole. Fine. Now see, since it is a small magnet, some dipole moment will be associated with this, because if you remember in electrostatics also, when we discussed about dipoles, plus q charge, minus q charge, separated by a small distance 2a, then the dipole moment is given by p. Okay, and the direction of this dipole moment is always from negative to positive. Here also, since it is behaving like a small magnet, suppose like this side is suppose n pole, this side is s pole, then they are separated by a small distance, so there will be some dipole moment, and this dipole moment in this case is given by m, which is a vector quantity. So here a small magnet, when we consider, the south pole resembles with the negative charge, north pole resembles with the positive charge, so the direction of dipole moment will be from south to north. Okay, the direction of m is from south to north. So that means for this kind of loop, south pole is where? South pole is down, below, north pole is up, so magnetic moment will be from down to up. This one, see here it is drawn, the magnetic moment, this one, down to earth, because this direction and this direction is same only, no? Then for this kind of loop, this is the direction of current, this direction same. So here magnetic moment will go from south to north. So south is the upper surface, north is the lower surface, so it goes like this. Okay, now the magnitude of M, that is the product of current that is flowing through the loop and the area of the loop, that is the product of area and current gives us magnetic moment, or area can be written as pi r square. So I into pi r square gives us magnetic dipole moment. Okay, this one. Now about the direction I told you. So the unit of magnetic dipole moment will be ampere meter square, and the dimensional formula is this one. Okay, so this thing you remember. Next let us move to this topic. Here what we are going to discuss is, suppose there is an electron and the electron is moving on some circular orbit. Suppose this is the electron. So if this is the electron, the velocity of the electron is like this, tangent velocity. Current is in the opposite direction, like this. Now see, this loop is behaving like a current carrying loop. In the previous case just now what we discussed, that if it is a current carrying loop, what shall we write here? The thing will be like this, no? Current this side. So here if we write S and if you put the arrows, then it is matching this arrow, this arrow. That means the upper surface is south pole, lower is the north pole. What will be the direction of magnetic dipole moment then? Upward to downward. So this is the direction of magnetic dipole moment. In this particular case, it is given by mu. Instead of m, they have used mu, okay, or mu l. Now this is the case. This is the thing. Electron moving this side, velocity vector. Current opposite side. Dipole moment, this one, given by mu l. Okay. Another thing will be here, that is angular momentum. Angular momentum is this formula in class 11 you got, r into m, r into p actually means momentum, r into mv, r cross. So since it is a cross product of r and v, so the plane containing r and v, this direction of L will be perpendicular to the plane containing r and v. So r is the radius, this is r, this one, okay, v is this one. So in which plane they are containing? They are containing in this plane. So the direction of L or magnetic dipole, this one momentum, angular momentum, this will be in upward direction, perpendicular. Now here we are here to find out an expression for dipole, expression for magnetic dipole moment. So we'll start with this equation. Current. We know current is equals to charge by time. So charge means here it is the charge of electron. Time means for one complete rotation the time is time period. Again we know S is equals to Vt. So from this T is equal to S by V. So for a complete rotation, for one complete rotation, S means it is the circumference, which is 2 pi r, and V will remain this one. So 2 pi r by V is the value of T. This value we can substitute here. So this thing becomes I is equal to E by T, means this value, this one, okay, and V will go up, so this one. Now we need magnetic dipole moment mu. Just now I told you that it is the product of current and area. So current, this one, area pi r square. If you calculate, the value comes this one. Okay. So this is an expression for magnetic dipole moment, but actually we want to represent this magnetic dipole moment in terms of L. So what shall we do now? This expression can be written as E by 2m into mvr. Same only, this m gets cancelled. What we are getting? EVR by 2, this one. Why we are doing so? So that in place of mvr we can write L. So the thing, in place of this we can write E by 2m into L. Okay, this one. Alright. Now since this is also another expression of mu, but we can express it in vector form also, putting one vector here and putting one vector here, negative sign for negative charge of electron. Okay, then as this L comes down, mu L by L, this one, in right hand side what we'll have except this negative sign, you forget about that. The magnitude is E by 2m. So E by 2m is a constant number. E means the charge of electron, m mass of electron. Then if these constant values are substituted, we get this a constant number. This number, it has a unit, coulomb per kg. This value is called gyromagnetic constant. Fine. Now from this formula again, what we are doing, in place of L we are substituting this value. L is angular momentum, and we know from Bohr's postulate L is equal to integral multiple, means n into h by 2 pi, where n is the number of shells, number of orbit, 1 2 3 like that. H is Planck's constant. So this value we will substitute here in place of this L. So if we do so, okay, this one, in place of L we have written this value. So except n, here all the other terms are constant. So n is keeping it outside. Other terms we are keeping inside a bracket. Since these things are constant, E, H, these all are constant values. This constant is called Bohr Magneton. This can be a unit. This Bohr Magneton, it is generally denoted by mu b, and it serves as a natural unit of magnetic moment. Why? Because you can see, as the electron is in the first shell, n will be 1, this value will be same only. Electron in the second shell, this value will be 2, but this will be same. So that means mu can be written as either it is 1 Bohr magneton, or it will be 2 Bohr magneton, 3 Bohr magneton. So Bohr magneton can be a unit of mu l. Okay, and it has a value. As I told you that these values are constant, these are some constant numbers. So if we substitute the values of this constant number here, we get another constant value, 9.27 into 10 to the power minus 24 ampere meter square. This is the value of Bohr magneton.